Hello, and welcome to Night Cosmos Sleep. Thank you for setting aside a quiet moment in your day to pause here. Sometimes, we do not need more noise or more things to remember. We only need a slow, gentle voice to carry the mind away from the hurried rhythm of the world outside. Imagine a photograph being opened very softly. Not the kind of image that makes an immediate impression, but one that asks us to look a little longer. Somewhere within the frame is a small detail, so faint that it could almost be overlooked. Yet if we remain with it for a few more seconds, we begin to realize that its dimness is not necessarily emptiness. Sometimes it is only the beginning of a story that is very distant, very vast, and very quiet. That is also how we begin today's journey, from a faint streak of light to a giant galaxy. From one small sign that seems almost insignificant, the story will slowly unfold into the deeper layers of the universe. There is no need to rush to name everything, and no need to fill your mind with numbers. You only need to listen gently, allowing each image to arrive and then drift away, while the rhythm of the narration finds a quiet place within your own rest. Some discoveries in the universe begin with a very small detail, not with a scene that immediately reveals the scale of what we are seeing. Sometimes, they begin with nothing more than a scientific image opened on a screen, filled with countless points of light, broad regions of darkness, and one faint mark near the edge of the frame. That dim mark can easily slip past the eye. Nothing about it seems unusual enough to hold our attention for more than a moment. Among the many lights in the image, it appears only as a region slightly fainter than the rest, so soft that it almost dissolves into the background. Without someone pausing to examine it carefully, it might be dismissed as an unimportant part of the image and overlooked along with hundreds of other small details. In astronomy, however, a feature like this cannot be ignored too quickly. Many objects at great distances do not appear clearly at first. They may show themselves only as a tiny spot, a faint streak, or a patch of light that looks slightly different from its surroundings. The human eye may treat such a difference as insignificant, but to those who observe the sky through telescopes, that subtle variation can sometimes be the first sign of something enormous. We can understand this through a more familiar image. When we look at a city from very far away, its lights no longer separate into individual streets or windows. Everything blends into one faint glow. But our inability to see the details does not mean the city is small. It simply lies too far away for our eyes to distinguish its individual parts. A distant galaxy can appear in much the same way. Within it may be countless stars, clouds of gas and dust, and regions where new light is being born. But when that light must cross an immense distance before reaching us, an entire system of stars can be reduced to a small, faint mark in an image. What looks like a blur may actually be the combined light of a whole galaxy. The first important idea to hold on to is this. In the universe, faint does not always mean small. Some objects appear weak because they truly produce little light, but others appear weak simply because they are so far away. Distance thins the light, softens the shape, and transforms something vast into a very small sign within the range of human vision. When an observer notices such a faint feature, they cannot immediately call it a galaxy. First, they need to determine whether the light is real or merely an error in the image. Does it appear again in other observations? Does it remain in the same position? Does its light spread in a different way from that of a closer star? These checks allow human understanding to move slowly from uncertainty toward knowledge. This is how science approaches things that are extremely far away. A strange streak of light does not instantly become a discovery. Before an object receives a name, it usually begins with caution, looking again, comparing again, measuring again, and only then gradually recognizing what it may be. That slowness does not make the story less interesting. On the contrary, it gives an ordinary faint mark the chance to become reliable evidence. It is a little like returning to an old photograph. At first, we may notice only the person standing in the center, but when we look more carefully, we begin to see a house in the background, a narrow road, or a chair resting on the porch. These details are not the center of the image, but they help us understand the wider setting. They show us that the story within the photograph extends beyond what first caught our attention. The faint mark in an image of the universe may work the same way. It might lie near the edge of the frame, small and dim, but if it is truly a galaxy, then behind it is more than one isolated point of light. It may be the blended glow of countless stars held together within a vast system by gravity. From our distance, the individual stars can no longer be separated. Their light merges into a weak patch that nearly disappears into the background. We often remember galaxies through beautiful images in which spiral arms and luminous regions appear with remarkable clarity. But when a galaxy is first identified, it does not always present itself in such a complete form. Often, it begins as nothing more than a slightly unusual brightness within the data, a small sign that is just different enough to make someone look again. From that sign, the story begins to expand. If it is real, how far away is it? If it is a galaxy, how long has its light been traveling? At the beginning, however, we do not need to answer everything. It is enough to understand that a small detail may deserve a longer look. The universe often opens itself through signals like these, very faint, very distant, and not immediately clear. Human beings do not enter that mystery through haste, but by preserving one small detail, examining it carefully, and allowing understanding to grow brighter one step at a time. So for now, we can remain with that single moment, an image observed more closely, a faint mark finally noticed, and one very simple question beginning to form. What if the thing that looks so small is not small at all? What if its dimness is only distance softening the light of an enormous galaxy? That is where our journey begins. It does not require an overwhelming opening or a mind filled with numbers. It needs only a small streak of light near the edge of an image, and an observer patient enough not to dismiss it too soon. If we remain a little longer with the faint mark near the edge of the image, we begin to notice something very simple, yet easy to forget. The human eye does not see an object only through the light it produces. It also sees that object through distance. A car's headlights at the far end of a road are not small lights. They are simply far away. When the car is closer, we can distinguish the two beams, see the road reflecting their glow, and watch the shape of the vehicle move past the darkness along the roadside. But as the car travels farther away, all those details begin to contract. The two headlights merge. The body of the car disappears first. Then the light itself becomes smaller, weaker, and softer, until only a thin point remains at the end of the road, trembling slightly in the darkness. Nothing about the car has actually become smaller. What has changed is the distance between it and our eyes. The universe often misleads human perception in the same way. An object may be enormous, brilliant, and extraordinarily complex where it exists, but when its light crosses an immense region of space, it no longer reaches us as a complete image. It arrives as what remains: a sign. A streak of light made thin by an impossibly long journey. That is why a faint mark in a deep space image cannot be dismissed simply because it is dim. It may be faint because it is intrinsically weak, but it may also be faint because it is extremely far away. A galaxy at a great distance from Earth does not enter an image carrying its full vastness. It does not bring every individual star into view. It does not immediately reveal its dust lanes, clouds of gas, young, luminous regions, or dense central structure. Distance gathers all those features together, softens them, and delivers them to us as one small patch of light. We can imagine a city at night seen from high above. When an airplane is still flying at a relatively low altitude, the details remain vivid. We can see illuminated roads crossing neighborhoods. In some places, streams of headlights form bright lines. Some districts are densely lit, while others are more scattered. Dark regions mark parks, rivers, lakes, or suburbs where fewer lights are shining. At that height, the city still looks like a city. It has shape, movement, and many different layers of light and shadow. But as the airplane climbs, each detail begins to withdraw. Streets no longer look like distinct streets. Cars no longer appear as individual vehicles. Bright windows no longer belong to separate rooms. The entire city slowly becomes a soft glow beneath the clouds, like a patch of golden light resting quietly on the ground. From even higher above, that glow may become nothing more than a tiny point surrounded by vast darkness. To someone sitting inside the airplane, it is only a patch of light. But for the people living below, that light contains homes, dinners, conversations, workplaces, hospitals, train stations, appointments, and sleep that has not yet become deep. Distance does not erase the life inside the city. It only prevents the distant observer from separating one part from another. A galaxy can also be reduced by distance in this way. If we could move closer, if we could somehow see beyond the limits of human vision, we would discover that it is not simple at all. It might be an immense city of stars, where billions of suns exist together within a shared gravitational system. Some regions may be brighter, where stars are gathered more densely. Others may appear darker, where clouds of gas and dust block part of the light. In some places, young stars have only recently formed, burning hot and bright. Elsewhere, older stars glow with warmer, quieter light, carrying the long memory of the galaxy. But from Earth, when the distance is too great, all those layers blend together. The light from countless stars, clouds of gas, and internal structures no longer arrives separately. It merges into a common glow. And after crossing an enormous expanse of space, that shared light may appear in an image as nothing more than a faint blur. This is why our first impressions can so easily be misleading. We often assume that whatever appears brighter must be more important, that whatever looks larger in an image must also be larger in reality, and that whatever seems faint is probably small or too distant to deserve attention. But in astronomy, an image does not always speak through familiar intuition. A nearby star may appear far brighter than an entire distant galaxy. A small, sharp point may be only one star within the Milky Way, while a weak blur beside it may contain the combined light of countless stars in another galaxy. Even the Milky Way, the galaxy that contains our solar system, is not a small place. It may contain somewhere between 100 and 400 billion stars. There is no need to hold that number in the mind like a calculation. We only need to consider, slowly, that the sun, the star illuminating our days, is merely one among all those stars. And if an observer from an extremely distant location looked toward the Milky Way, all those stars, planets, clouds of gas, regions of dust, and spiral arms might also blend together into one soft streak of light in their image. Once we think this way, the faint mark at the edge of the frame no longer seems meaningless. It becomes a possibility. There may be an enormous structure inside it. Its light may not be weak because the place itself is small, but because it has crossed an extraordinarily long distance. What we are seeing may not be a simple point of light, but the thin remains of an entire city of stars after distance has taken away almost all of its detail. Distance spreads light outward. The farther it travels, the more diluted it becomes to our eyes. It is a little like a voice calling from the far end of a long street. The person may be speaking clearly where they stand, but by the time the sound reaches us, it has weakened, softened by wind, buildings, and empty space. We still hear it, but many of its original details are gone. Light from a distant galaxy reaches us with a similar gentleness. It does not vanish completely. It simply becomes thinner, more difficult to read, and more dependent on patience. Looking into the universe is therefore not only a matter of noticing what shines most brightly. It also requires learning to question our first impressions. A weak signal may be speaking of something enormous. A tiny blur may be the remnant of a journey of light far longer than any human lifetime. A dim region in an image may not be empty or insignificant. Distance may simply have turned it into a whisper. If we stand close to a city, we hear traffic, see signs, and notice individual stores opening their doors. From farther away, we see only its light. From farther still, the entire city becomes a point. Yet no one would say that the city has disappeared simply because it has become smaller within our field of view. It remains there, filled with streets and lives. Only our ability to distinguish what lies inside has changed. A distant galaxy is the same. When it appears as a blur in an image, that is not the end of its story. It is only the beginning. The blur tells us that its light has reached this place, however faintly. It tells us that somewhere in space, a vast system exists, or once existed when that light began its journey. It tells us that human beings are not looking at something nearby, but at a signal that has crossed an immense distance before touching the detector of a telescope. And once we understand this, the way we look at the image begins to change. Faint streaks are no longer merely part of the background. Weak points are no longer dismissed as visual noise. They become reminders that the universe contains layers far deeper than our first impressions suggest. Some things must be seen through time, measurement, comparison, and a kind of patience that the unaided eye cannot possess on its own. A person standing on the ground and looking into the sky with the naked eye sees only a very small part of the story. Human vision is beautiful and sensitive within everyday life, but when faced with light that has traveled too far, it is like a small cup placed beneath a very gentle rain. The rain is there, but the cup cannot collect very much. The light is there, but the eye is not large enough, patient enough, or sensitive enough to gather it into a clear image. If distance can reduce a city of stars to a faint mark, then human beings need more than a passing glance. We need a way to collect light for longer. We need larger eyes that know how to wait and gather weak rays rather than allowing them to pass too quickly. And this is where the story leaves the limits of human vision and moves toward the telescope, a quiet instrument that not only allows us to see farther, but also helps us preserve the fragile light that has traveled through darkness for so long. Once we understand that distance can reduce an entire city of stars to a faint mark, we begin to realize that the problem does not lie only in that distant place. It also lies within our own eyes. Human vision is remarkably refined in everyday life. It allows us to recognize the face of someone we love in a crowd, read small lines of text on a page, notice the color of a shirt as someone crosses the street, and distinguish the light of morning from the gentle golden glow of evening. In a familiar room, even a little light slipping through a doorway may be enough for the eye to recognize a table, the edge of a chair, or a cup of water beside the bed. These eyes have accompanied humanity through countless familiar moments. They help us find our way along a street, watch the shadows of trees move across the ground, and recognize the red of an apple or the green of leaves after rain. For life on Earth, human sight is an extraordinary gift. It requires very little conscious effort. We simply open our eyes, and the world immediately takes on shape, color, and distance. But when we look into the deep universe, that gift suddenly seems very small. Not because human eyes are poor, but because light from extremely distant places does not reach us in a familiar way. It is not like light inside a room, sunlight reflected from water, or the headlights of a car at the end of a road. Light from a distant galaxy has crossed an immense expanse of space. During that journey, it becomes thinner within our field of view. By the time it reaches Earth, only a very small amount may remain. Too little for ordinary eyes to gather into a clear image. We can imagine the human eye as a small cup placed outside on a porch during a light drizzle. The rain is still falling. The air is not dry. Droplets continue touching the roof, the stone floor, and the leaves in the yard. But if a small cup is left there for only a few seconds, almost nothing has collected at the bottom. A few drops may have entered, but not enough to form a visible layer of water. It is not because the rain is absent. The cup is simply too small, the time is too short, and the rainfall is too gentle. Human eyes receive the distant light of the universe in much the same way. The light is still arriving. It continues to arrive without pause. But our eyes collect only a very small portion of it. Some rays are too weak, some signals too thin, and some objects too distant for the naked eye to see anything but darkness. Yet that darkness does not necessarily contain nothing. Galaxies, stars, gas, dust, and regions where new stars are forming may still be there. The amount of light reaching human vision is simply not enough to give them a recognizable shape. This makes the night sky seen with the naked eye both beautiful and limited. When we look upward, we may see a few bright stars, the faint band of the Milky Way from a truly dark place, the moon, several planets, and a few familiar constellations. But this is only a very small part of the picture. Beyond everything our eyes can see, countless other signals are still traveling through space. They pass through the sky above us without appearing naturally within ordinary human vision. One reason is that human eyes can detect only a narrow range of light, known as visible light. This is the portion that creates the colors familiar to us: red, orange, yellow, green, blue, violet, and all the shades between them. In everyday life, visible light seems almost sufficient to make the world feel complete. But the universe does not speak only through the light human beings can see. It also produces signals in infrared, radio waves, X-rays, and many other forms of radiation. These signals are not unusual or unimportant within the universe. They are essential parts of its story. Cold regions of dust inside galaxies may remain difficult to see in visible light, but reveal much more in infrared. Clouds of gas, stellar remnants, and regions of intense energy may not tell their stories through familiar colors, but through other forms of light. If we depend only on human vision, we are like someone standing before a vast piece of music while hearing only a few notes in the middle. The rest is still being played. Our ears simply cannot hear it. This is why the faintness of a distant galaxy does not come only from distance. It also comes from the limitations of the way we see. Some of its light may be arriving in a form that ordinary eyes cannot detect. The object may shine more strongly in infrared. Dust may be blocking part of its visible light. Its clearest signal may lie outside the narrow range that human eyes evolved to perceive. This understanding gives us a greater sense of humility. We live within a universe that is not silent, yet ordinary human vision receives only a small part of what it is saying. The universe is not always hiding from us. Often, it is sending signals steadily and continuously. We simply need another way to receive them. Like the small cup on the porch, if we want to understand how much rain is truly falling, we cannot judge by the few drops collected after only a brief moment. We need a larger container. We need to leave it outside for longer. We need to allow time to do its work. Then the separate droplets begin to gather. A surface of water appears. The porch light begins to reflect in the thin layer. Something that once seemed absent gradually becomes visible. Human beings followed the same path when looking into the universe. When the naked eye was no longer enough, we did not stop. We built larger eyes. Not eyes of flesh, but wide mirrors, sensitive detectors, and instruments capable of waiting longer than a person can wait, collecting more light than a person can collect, and detecting forms of light that human eyes cannot see. These instruments do not make the universe more wondrous. The universe was already wondrous. They simply help us recognize what has always been there. A faint mark in an image does not suddenly gain meaning because we give it a name. That meaning was already carried within the light. A telescope merely holds on to that light long enough for human beings to read it. The limits of human vision are therefore not an ending. They are the beginning of curiosity. Because our eyes are small beneath such a thin rain of light, we learned to create larger bowls. Because we cannot see everything, we came to understand that the sky is deeper than what appears on a clear night. And because a faint mark cannot tell its entire story to the naked eye, humanity learned to depend upon the patience of telescopes. From the small cup of human vision, the story moves toward the larger vessel of deep observation. There, light is no longer allowed to pass unnoticed so quickly. Weak rays are collected one by one, faint marks are held for longer, and what once dissolved into darkness is finally given the chance to appear, not through haste, but through a kind of patience that feels very close to the rhythm of the universe itself. If the human eye is like a small cup that catches only a few drops of rain, then a telescope is a large bowl resting quietly beneath a thin shower of light, patiently collecting each ray from the most distant regions of the universe. Photon by photon, the light strikes the mirror, reaches a sensitive detector, and slowly accumulates. One layer of data is placed upon another until faint objects that the naked eye could never see begin to emerge. Inside the darkened room of an observatory, light from a distant galaxy arrives like tiny grains of dust. It makes no sound and offers no sudden brilliance. The unaided human eye collects only a very small portion of it, like a cup placed beneath the rain. But this larger bowl of light, wider, more sensitive, and more patient, holds on to much more. It gathers every blurred streak and every dim point until the gentle outline of a stellar system slowly appears, with a denser, brighter core and outer edges spreading softly into the darkness, revealing a picture the naked eye has never seen. An ordinary image can help us understand this patience. Imagine a bowl placed outside on the porch during a light drizzle. At first, there is only moisture. After a little while, a few drops fall into it, collecting and stirring small ripples across the bottom. Wait longer, and the surface of the water begins reflecting the porch light, making the glow clearer. Patience and time transform something almost insignificant into a scene that can be recognized. A telescope works in much the same way. It knows how to wait. It knows how to hold. It gathers the fragile signals of the universe and gradually gives them form. What makes a telescope powerful is not only its ability to see farther, but also its ability to wait. The primary mirror of the James Webb Space Telescope is about 6.5 meters wide, making it an enormous bowl for collecting light. Because of this, faint objects no longer pass too quickly into darkness. Their weak light can be held long enough for human beings to recognize structure, shape, and even the activity taking place within them. Dim regions in an image are no longer isolated marks. They become meaningful signs, gradually leading us toward an understanding of a vast, complex, and dynamic system. Another scene begins to form in the mind. Imagine looking at a neighborhood at night through the window of an airplane. When the plane is flying low, individual streetlights are visible, and cars can be seen moving along the roads. As it climbs higher, the details begin blending together into a soft region of light. Higher still, the entire neighborhood becomes only a thin, glowing point. The telescope's bowl of light is like that airplane, moving high above while still preserving detail, gathering small amounts of light from many places so that the picture does not lose its sense of life. Within the stillness, as the data slowly accumulates, we begin to recognize what ordinary vision cannot see: the curve of a spiral arm, dark regions between stars, young stars beginning to form, and even traces of galaxies farther away. Every layer of data and every observation is one slow step in returning distant light to human understanding. And once the light has been gathered, the next question is not only where it came from, but how long it traveled and what it experienced along the way. A telescope patiently collects each photon so that the light can tell its own story. It reminds us that the universe does not always appear in the way we expect. It arrives little by little, according to its own rhythm, and only when we listen patiently do we begin to read what it is saying. From the small cup of the human eye to the great bowl of the telescope, the story continues to open wider. The original faint mark is now part of a complex system of light, one fragment of a much larger galactic picture. And through that patience, the dim streak near the edge of the image begins to tell its true story. A story the naked eye could never read alone, but one that gradually reveals the vastness and subtle beauty of the universe through time and careful observation. The light in an astronomical image does more than tell us that an object is very far away. It also tells us that we are looking at a moment that has already passed. This is one of the most important things to understand when observing the universe. Light needs time to travel. For nearby objects, that time is so brief that we barely notice it. But for distant galaxies, the journey of light to Earth can last millions or even billions of years. In everyday life, we rarely feel this delay. When we turn on a lamp, the room seems to brighten almost instantly. When we look at a table, a cup, or the road ahead, it feels as though those images are reaching our eyes in the present moment. In reality, light still needs time to travel from an object to our eyes, but the distance is so short that the delay is insignificant. Our natural impression is therefore simple. When we see something, it is there before us exactly as it is now. In the universe, that impression is no longer entirely correct. The distances between celestial objects are enormous. Light from the sun takes several minutes to reach Earth. This means the sunlight touching our hands is not light that left the sun at the exact moment we became aware of it. It has already completed a short journey through space before arriving here. In the case of the sun, a delay of several minutes is still easy to understand. But when we speak of a distant galaxy, the travel time of its light can extend far beyond every timescale familiar to ordinary life. The Andromeda Galaxy offers a clear example. It lies about 2.5 million light-years away. This means the light from Andromeda that we see today left that galaxy roughly 2.5 million years ago. When the light began its journey, Earth was nothing like the world we know today. Cities, telescopes, computers, and the person looking at the image now did not yet exist. Yet the light continued traveling across an immense span of time until it was finally recorded by human eyes or observing instruments. When we look at a distant galaxy, then, we do not see it exactly as it exists at this moment. We see it as it once appeared when the light departed. This is what the phrase, "looking far away," means looking into the past, truly means. The farther we look, the older the light becomes. The farther we look, the earlier the period of cosmic history revealed to us. This does not make an astronomical image any less real. The light we receive is genuine light from a real object. But it is old light. It is like a photograph that arrives late. The image still records a moment that truly happened, but that moment no longer belongs to the object's present. A galaxy may have changed during the time its light was traveling toward us, yet the image we receive preserves its condition at the moment that journey began. We can imagine light as a letter. When the letter rests on a table, we hold it in the present. But the words inside belong to the moment when the sender wrote them. The sender may have changed. The room in which the letter was written may no longer look the same. Yet the letter still preserves information from that earlier time. Light from a distant galaxy works in much the same way. It contains no written sentences, but it carries information about the place that produced it, its brightness, its color, and part of the object's shape. In addition to needing time to travel, light from distant galaxies carries another important sign. Before introducing the term, we can understand it simply. Light has a wavelength. If the space between us and a distant galaxy expands while the light is traveling, that wavelength can be stretched. As the wavelength becomes longer, the light shifts toward the redder end of the range measured by astronomers. This sign is called redshift. It is an important term in astronomy. It does not mean that every distant object literally turns red in the way our eyes might perceive color. It means that its light has been stretched toward longer wavelengths. Because red lies at the longer wavelength end of visible light compared with blue, the effect is called redshift. A familiar comparison is the sound of a vehicle moving away. As the source of the sound recedes from the listener, the sound may seem lower and deeper. Light is not sound, but the idea of something being stretched as the source moves away and the distance changes can help us form a basic picture. In light from a distant galaxy, that stretching is evidence that the light has crossed an enormous distance through an expanding universe. Redshift helps astronomers learn more about the object they are observing. It suggests that the light may have traveled a very great distance. It is also important evidence that the universe is expanding. When scientists measure the light from many distant galaxies, they find that the farther away a galaxy is, the more strongly its light is generally shifted toward the red. From this, they can estimate distance and learn more about the history of motion within the universe. For an ordinary viewer, there is no need to remember formulas or calculations. The important idea is this: the color of light is not only something beautiful to see, it can also carry information. A faint streak may help reveal how distant an object is, how long its light has traveled, and how the universe has affected that light along the way. Once we understand this, an astronomical image becomes much deeper. Within a single frame, light may be arriving from many different moments in time. A nearby star sends us newer light. A distant galaxy sends us light that is far older. They appear together on the same screen as though they exist side by side, yet they may belong to very different layers of cosmic history. A faint streak, then, is not merely a small mark in an image. It may be a signal that has crossed an immense distance. It may be an image of a galaxy as it existed millions or billions of years ago. Distance may have weakened it, the expansion of space may have stretched its light, and only then was it finally captured by a telescope. This way of seeing helps us understand why astronomers do not ask only, "Where is this object?" They also ask, "When did this light leave it? How long has it been traveling? How much has it been redshifted? What do its color and brightness reveal about its distance?" These questions transform a faint mark into a true source of information. The dim feature near the edge of the image now carries another layer of meaning. At first, we learned that it might be faint because it is so far away. Then we learned that the human eye cannot gather enough of its weak light. A telescope allows that light to be collected for longer. And now we understand that the light also carries time. It does not come only from a distant place, but from a distant moment. As this letter of light is read more carefully, the next question begins to appear. If the light comes from a galaxy, what shape does that galaxy have? Is it merely a single point, or does its light spread softly because a wider structure lies within it? Does it have a brighter core? Do its outer edges gradually fade? From its color, brightness, and earliest visible shape, we begin to move into the next part of the story, recognizing that a blur is no longer only a blur, but may be carrying the first visible outline of a galaxy. Once the light has been captured by a telescope, a faint streak in an image is no longer just a single point of light. When the data is enlarged and processed carefully, the streak begins to reveal small details: a brighter core, fainter outer edges, a slight tilt, or a stretched shape. These features show that the object is not simple, but has a more complex structure, different from a single star. A star usually appears as a compact point of light, with sharp edges and almost no spread around it. A distant galaxy, by contrast, often looks softer, with its light spread more broadly and fading gently into the surrounding area. That soft spread is not an error in the image. It is one of the first signs that this is a vast stellar system. It contains millions, even billions, of stars held together by gravity. Astronomers distinguish stars from galaxies by the shape of the light, how much it spreads, its color, its spectrum, and the way the object appears across different wavelengths. An everyday image can help make this easier to picture, a drop of ink on paper. At first glance, it looks like nothing more than a blurred stain with no clear shape. But if you keep looking, the darker and lighter parts begin to stand out. The direction of the spread becomes clearer. The outer edges start to take shape, and you can tell which way the ink fell and how it spread. In much the same way, a faint streak in an astronomical image begins to show structure. A bright core, diffused outer edges, the direction of the light, and subtle but distinct color all come together to form the object's first visible shape. These details allow the observer to begin identifying what the object is. The streak is no longer an anonymous blur. It now has a core, an edge, a degree of spread, a direction, and a certain tilt. These traits do not yet reveal the object's entire internal structure, but they are enough to distinguish it from nearby points of light or from noise in the data. A blurry streak may look like a simple dot at first, but under careful analysis, it reveals itself as the combined light of many stars, blending together into the soft shape of a galaxy. This process of recognition does not happen in a single moment. It takes several steps, comparing the streak with other points of light, checking it across multiple wavelengths, observing it more than once, and repeatedly testing the data. When all of those pieces line up, the faint streak gradually becomes trustworthy as a real object. It can then be identified as a galaxy, with an initial shape, a brighter core, fainter outer edges, and sometimes a slight tilt or stretching along one axis. This creates the feeling that the dim streak is slowly coming into view. It does not suddenly flare up or become brilliant all at once. It appears gradually, layer upon layer, much like a stain of ink on paper slowly revealing its lines and shaded regions. The observer needs time to recognize the difference between a single point of light and a much larger object. Once the streak begins to take shape, the next step is realizing that galaxies do not all share the same form. Some galaxies are round and gentle, with light spread evenly throughout. Some are spiral galaxies, with curved arms winding outward. Others are distorted and uneven, stretched by gravity or by interactions with neighboring galaxies. The first faint streak only tells us that there is structure. But once we look at more galaxies, we begin to see the diversity in their shapes and arrangements. A faint streak, then, is no longer meaningless. It contains information about a bright core, outer edges, the direction in which the light spreads, its color, and the degree of its blur. That is enough for astronomers to identify the object, estimate its distance, and recognize that it may be a galaxy. It is also an important step in moving from the sight of a single point of light to the recognition of internal structure, gradually building a broader picture of the star cities that fill the universe. For an ordinary viewer, realizing that a blurred streak has shape makes the image feel more intuitive. We begin to understand that those soft, bright patches in an image are not mistakes. They are signs of a real object with structure, one that simply needs time and care to be recognized. Once the streak begins to take form, people naturally start asking the next questions. How many different shapes can galaxies have? How do spiral arms develop? Where are the bright young regions? And how do dark lanes of dust create shadowed areas? Through this process, a simple faint streak begins to develop a face. It is no longer just a nameless dim point of light. It shows a core, outer edges, a direction of spread, and an overall shape. Those small signs are enough to move into the next stage: classification, closer observation, and recognition of the diversity of galaxies. The original streak was only a sign. Now it has become important information for understanding the structure, history, and shape of a star city in the universe. Galaxies do not come in only one shape. In many astronomical images, some appear as bright disks with arms curving around a central region. Others have no clearly visible arms and resemble round or oval patches of light, softer and more evenly distributed. Still others follow no obvious order at all. Their light may appear uneven, distorted, or stretched, like a cloud that has been pushed out of shape. These differences do more than make images of the universe beautiful. They reveal that every galaxy has a history of its own. The type most easily recognized by many people is the spiral galaxy. A spiral galaxy usually has a brighter central region, with luminous arms curving outward like flowing streams. Within those arms are stars, gas, dust, and many regions where new stars may be forming. Because of this, spiral galaxies often appear especially active, as though the entire city of stars were turning very slowly within the darkness. Our own Milky Way is also considered a barred spiral galaxy, although we cannot travel outside it to photograph its complete shape from a distance. Another type is the elliptical galaxy. These galaxies are usually round or oval, with light distributed more smoothly and no clearly defined spiral arms. If a spiral galaxy resembles a city with broad roads, a central district, outer neighborhoods, and streams of light curving into the distance, then an elliptical galaxy is more like a quieter mass of light, with fewer visible lines and features. Many elliptical galaxies contain large populations of older stars and less cold gas from which new stars can form. As a result, they often appear less detailed than spiral galaxies in images made with visible light. There are also irregular galaxies. They are not evenly round, clearly oval, or decorated with balanced spiral arms. Their light may be concentrated more heavily on one side, stretched outward, broken into several regions, or shaped like a luminous cloud without any familiar form. Some irregular galaxies may have been affected by collisions or gravitational interactions with other galaxies. When two galaxies pass close to each other, gravity can pull gas, dust, and stars away from their original positions, leaving both systems more distorted. The important point is that shape is not merely appearance. It is a record of formation and development. A galaxy that still contains plenty of cold gas may continue producing many young stars. Regions of young stars often shine strongly in certain colors, giving the galaxy a fresher appearance with more visible structure. A galaxy that has used up much of its cold gas, or has experienced several mergers in the past, may become rounder and more uniform, with fewer clearly visible regions of new star formation. When astronomers study the shape of a galaxy, they do not simply describe it as beautiful or unusual. They examine where the light is concentrated, how bright the central region is, how the outer edges spread and fade, whether spiral arms are present, whether dark lanes of dust cross the galaxy, whether there are blue regions filled with young stars, or whether most of the light comes from older stellar populations. From these features, they begin to understand the galaxy's stage of development, the events it may have experienced, and whether it is still capable of producing many new stars. We can imagine galaxies as cities viewed from an immense distance. Not every city is built in the same way. Some have a clearly defined center, major roads extending in many directions, and broad outer districts. Others resemble older urban regions, dense with warm lights and structures that change very little. Some are expanding unevenly, brighter on one side and darker on the other, as though they have recently passed through a period of construction or disruption. From far away, all of them appear only as light. But when examined carefully, the way that light is distributed reveals a great deal about the activity within. A spiral galaxy can resemble a city filled with many active streams. Its arms contain gas, dust, and young stars that create prominent regions of light. An elliptical galaxy may resemble an old city that has gradually settled, with more evenly distributed light and fewer new regions suddenly flaring into brightness. An irregular galaxy may be more like a place that has undergone a powerful transformation, its shape still unsettled, and its light no longer arranged in a familiar order. These are only images meant to help us understand, but they remind us that every shape has a reason. In reality, classifying galaxies is not always easy. Very distant galaxies may appear too faint for their details to be seen clearly. A nearby spiral galaxy may display its luminous arms with great clarity, but at a greater distance those same arms may blur together, leaving only a soft patch of light. A small or faint galaxy may resemble an uneven glow, requiring additional data before observers can determine its true form. The shape seen in an image is therefore only a beginning. It must be considered alongside color, brightness, the spectrum of the light, and observations made at multiple wavelengths. This brings us back to the original blur. When it first appeared, it was only a small mark of light. After being enlarged and processed more carefully, it began to show a core, an edge, and a direction in which its light extended. Then, by comparing it with many other galaxies, observers began to recognize that these features might place it within a particular group of shapes. It was no longer merely a distant object. It could be a city of stars with a structure of its own. A galaxy's shape can also change over time. A galaxy does not necessarily preserve the same appearance from the moment it forms until the present day. It can gather more gas, produce new stars, lose gas, collide with another galaxy, or merge with smaller stellar systems. Each event can alter its structure. A spiral arm may be pulled out of position. A small galaxy may be stretched apart. Two large galaxies may merge and become a new galaxy with a very different shape. The form we see is therefore not only a picture of the present, it is also the result of many stages that came before. Once we understand this, we begin to look at images of galaxies differently. A spiral is no longer only a beautiful pattern. A round glow is no longer merely a soft patch. A distorted shape is no longer simply disorder. Each appearance may preserve traces of gas, dust, young stars, old stars, rotation, and encounters from the distant past. The universe does not arrange every galaxy into a single design. It allows them to grow, interact, and change, while their shapes preserve part of that story. For the observer, this is an important expansion of understanding. From a faint mark, we recognize structure. From structure, we recognize shape. From shape, we begin to see that each galaxy has followed its own path. Some galaxies remain young and filled with newly bright regions. Others have become quieter, with their light spread more evenly. Some have been stretched, struck, or reshaped by gravity. These cities of stars differ not only in size, but also in how they have lived through time. Once a streak of light has taken on a shape, it opens a larger question. How many different kinds of star cities exist in the universe? The answer is not contained in a dry list. It is written within the images themselves. In some places, light curves into a spiral. In others, it gathers into a soft mass. Elsewhere, it is pulled out of alignment, broken apart, and distributed unevenly. Each form is one way in which the universe preserves its own history. From here, our attention begins to rest more closely on spiral galaxies. Among the many shapes galaxies can take, spirals often give the clearest sense of movement. Their luminous arms curving around the center are not motionless decorations. They suggest an extremely slow flow of stars, gas, and dust. And to understand how a galaxy can develop arms like these, we must move deeper into a spiral that never truly stands still within the darkness. Among the many shapes galaxies can take, spiral galaxies often leave the strongest impression. They have a brighter central region, with luminous arms curving outward like a current turning very slowly through the darkness. When we look at an image, it is easy to imagine the entire galaxy as an enormous wheel of light, its spiral arms rotating evenly around the center. But that picture is only partly correct. A galaxy does rotate, yet its spiral arms are not rigid bands of matter turning like the blades of a fan. A spiral arm is not a solid object. It is not a fixed ribbon of stars in which every star remains permanently attached to the same curved line. Instead, a spiral arm can be understood as a region of greater density within the galaxy's larger flow of motion. Stars, gas, and dust are more concentrated there than in the surrounding regions, making the area brighter and easier to see in an image. This distinction is important. If we imagine spiral arms as literal, solid arms, we misunderstand how a galaxy works. In reality, the stars within a galaxy continue following their own orbits around the central region. Gas and dust also move under the galaxy's shared gravitational influence. When they pass through regions of greater density, the light there becomes more prominent, much like a section of road containing more cars and more headlights, even though every vehicle continues to move. We can picture a city street at night. In certain places, traffic slows because of a red light, a narrow lane, or a crowded intersection. Seen from above, those sections appear brighter because more headlights have gathered together. But this does not mean the cars remain there forever. They simply pass through the crowded region, slow for a while, and then continue on their way. The spiral arms of a galaxy can be understood in a similar way. They are regions where matter becomes more concentrated, the light grows stronger, and star formation may become more noticeable. Gas and dust play important roles within spiral arms. Gas is the raw material from which new stars form. Dust can block part of the light, creating dark streaks or hazy regions within an image. As gas enters the denser regions of a spiral arm, it may become compressed. Under the right conditions, cold clouds of gas begin collapsing under gravity, producing regions of star formation. This is why the arms of many spiral galaxies contain especially bright areas where young stars cause the surrounding gas to glow. This helps explain why spiral arms are more than beautiful shapes. They are directly connected to the structure and activity within a galaxy. A bright arm may reveal a region where matter is more concentrated. A bluer patch of light may be associated with hotter, younger stars. A dark lane running along an arm may be dust blocking the light behind it. When we examine a spiral galaxy closely, we do not see only a circular pattern. We see layers of information about gas, dust, young stars, older stars, and the movement of matter. Another image that can help us feel this more clearly is a cup of coffee being stirred with milk. Before the milk has completely blended in, soft curved streaks appear across the surface. Some are darker, some lighter, and some bend gently with the rotating motion. These streaks are not fixed lines drawn onto the coffee. They are patterns produced by liquid moving, mixing, spreading, and changing over time. The spiral arms of a galaxy can create a similar impression, but on a scale that is incomparably larger and moving far more slowly. Still, we should not take the coffee comparison too literally. A galaxy is not an ordinary liquid. It is made of stars, gas, dust, dark matter, and gravity. These components do not blend together in the same way milk mixes into coffee. The image helps us understand only one essential point. Spiral patterns are not rigid, motionless objects. They are patterns appearing within a system that is constantly moving. Astronomers study spiral arms in several different ways. They observe visible light to see stars and dust. They use infrared light to look through some of the dust and detect older stellar populations or regions that would otherwise remain hidden. They use radio signals to trace cold gas, especially hydrogen, which is an important component of galaxies. By combining these different forms of data, they gain a clearer understanding of how spiral arms are connected not only to the galaxy's visible beauty, but also to the distribution and motion of matter within it. One idea worth remembering is that spiral arms are often connected with star formation. Not every new star is born inside a spiral arm, and not every part of an arm is forming stars intensely. But in many spiral galaxies, the arms are where denser regions of gas and dust, along with younger groups of stars, are easiest to see. Because young stars are often hotter and shine more strongly, they can make the arms appear especially bright in an image. The luminous curves of a spiral galaxy are therefore not merely decorative. They may reveal regions that are continuing to create new light. This also helps us understand why the spaces between spiral arms often appear darker or quieter. They are not completely empty of stars. Many stars still lie between the arms. But the concentration of gas, dust, and young stars may be lower, so those regions do not stand out as strongly. In an image, the contrast between bright arms and darker spaces creates the clear spiral pattern. In reality, however, The entire galaxy is one broad system in which stars and matter are distributed continuously, not confined only to the glowing curves. When examined more closely, spiral arms are not always even or perfect. Some galaxies have two large, clearly defined arms. Others have many smaller branches. In some systems, the arms are broken, displaced, or stretched by gravitational interactions with another galaxy. Some galaxies contain a bright bar across the central region, with spiral arms beginning at each end of that bar. Our own Milky Way is also a barred spiral galaxy, meaning its center is not simply a round concentration of stars, but includes a bar-shaped structure from which its arms extend. This diversity shows that a spiral galaxy is not a simple pattern. Its shape is the result of rotation, gravity, the amount of gas it still contains, ongoing star formation, and interactions from its past. The spiral form visible in an image is only the outward appearance of a much more complex process. It is like seeing ripples on the surface of water and understanding that movement is taking place below, even when the entire current cannot be seen directly. Spiral arms also change the way we think about the apparent stillness of astronomical images. A photograph makes everything seem motionless. The galaxy rests against a black background. Its arms do not move, and its luminous center appears unchanged. But this is only because human timescales are so short. On the timescale of a galaxy, everything is in motion. Stars are orbiting the center. Gas is flowing through denser regions. Dust is concealing and revealing light. New stars are forming inside cold clouds and gradually illuminating the space around them. When we look at a spiral galaxy, then we are seeing a structure that has both shape and motion. It is not a fixed painting. It is a system operating at an extraordinarily slow pace. The bright curves in the image reveal how matter and light were distributed at one particular moment. If we could observe the galaxy for millions of years, the image would change. Stars would continue moving. Regions of star formation would appear and then fade. The overall spiral form might remain, but the details within it would never stand still. This makes a spiral galaxy feel more alive. It is not beautiful only because of its curves. It is remarkable because those curves contain gas, dust, stars, gravity, and time. They reveal that a galaxy is not merely a collection of many stars, but an organized system with flowing motion and regions of different activity. From here, we can look back at the original faint blur in a different way. If that blur is a spiral galaxy at an immense distance, we may not be able to distinguish its individual arms. Distance may soften every detail. Yet the gentle spread of its light, its brighter central region, its color, and the way its brightness is distributed may still suggest that an underlying structure is present. In nearby galaxies, or in galaxies observed with greater clarity, that structure appears as curved arms. In more distant galaxies, it may remain only a very subtle sign. Between those bright arms, we often see dark streaks, regions where dust blocks the light, and hazy bands that prevent the image from appearing completely transparent. These darker areas are not meaningless emptiness. Often, they are curtains formed by cold dust and gas lying between the stars. To understand a galaxy more clearly, we must learn to look at both its luminous regions and its shadows. When we look at the spiral arms of a galaxy, not every dark region is truly empty. Some appear as soft gaps, shadowy bands cutting across the light. But in reality, these are not places where nothing exists. They are often made of cold dust and interstellar gas lying between us and the stars behind them. That dust absorbs part of the visible light, reducing the brightness that human eyes or ordinary telescopes are able to see. Because of this, part of a galaxy may appear darker, but that does not mean it is empty. With infrared telescopes, these thin curtains of dust become more transparent. Astronomers can look through them and detect regions where young stars are still being born, along with clouds of gas that have not yet begun to shine clearly in visible light. Infrared observations help reveal areas that ordinary light cannot easily pass through, uncovering activity inside a galaxy that the human eye cannot see. An everyday image can make this easier to picture. A thin curtain hanging in front of a window. The light outside is still there, but through the curtain it becomes softer and dimmer. The space behind the curtain does not disappear. The light is simply reduced, yet it still exists and can be seen if we use the right tools. Interstellar dust works in a similar way. It blocks part of the visible light, but it does not remove the object itself. These dark regions matter because they give clues about a galaxy's inner structure. Dust and gas may be concentrated there, creating the setting where young stars can begin to form. They also shape the way light from the stars behind them reaches our eyes. By observing the dark regions and the brighter areas around them, astronomers can estimate the density of gas and dust and predict which regions may give birth to stars in the future. So when people look at a galaxy, they do not see only brilliant stars or glowing spiral arms. They also see these soft curtains, these darker regions that hint at cold dust, gas, and star-forming activity that has not yet become clearly visible in light. These curtains make the image of a galaxy feel more three-dimensional in the human mind, revealing depth and complexity within it. Because of that, a galaxy is not just a painting made of light. It is a living system in which young light, old stars, gas, and dust interact with one another. When the streaks of light are studied carefully, we begin to realize that the dark regions are not empty at all. They are an important part of the background, helping shape and shield the galaxy, creating the rhythm of brightness and shadow between its spiral arms. These details also remind us of the limits of human vision and visible light. Many things exist within a galaxy that do not appear directly to the naked eye. Only with the right tools, such as infrared instruments, can an observer look through the dust, detect young stars, and recognize the regions that are quietly producing new light. In that way, dark regions are no longer meaningless, empty spaces. They are important parts of the structure, where the lives of new stars begin. Once we understand the role of dust and these curtain-like layers within a galaxy, we realize that the light we see is only part of the whole picture. There are bright regions, deep dark regions, and faint intermediate areas in between. Both light and shadow help tell the story of structure, motion, and star formation. A galaxy is not just a collection of bright points in an image. It is a system with depth, where light and darkness interact to create its own shape and rhythm. With this understanding, astronomers are able to describe galaxies in greater detail. Because of that, the image of a galaxy on a screen becomes more alive. It is no longer a simple flat picture, but a complex system with many layers, many motions, and many stories unfolding inside it. The dark regions within a galaxy are not always empty. Behind layers of cold dust and gas between the stars, an important process may be taking place, the formation of new stars. At first, this may seem to go against intuition, because we often imagine that light must begin in a bright place. But in the universe, many stars are born inside cold, dark, and dense regions where outside light has difficulty passing through. A star does not suddenly appear out of nothing. It begins with gas and dust in space. These clouds of gas and dust can be enormous, very cold, and extremely thin compared with matter on Earth. But in space, once enough material becomes concentrated within one region, gravity begins pulling it together. At first, this process happens slowly. One part of the cloud becomes denser. More material gathers there. As the density increases, gravity becomes stronger, drawing still more gas and dust inward. In simple terms, gravity is the attractive force between objects that have mass. In everyday life, we are familiar with Earth's gravity pulling things toward the ground. Inside clouds of gas and dust between the stars, gravity is also working quietly. It draws the denser parts of a cloud together, causing a smaller region within it to contract. As that region contracts, it becomes denser and hotter. If the process continues for long enough, the core of a young star begins to form. A dark region within a galaxy is therefore not necessarily lifeless or still. It may be a place where light is being prepared. Before a star shines clearly, it may spend time enclosed within a cocoon of gas and dust. The surrounding material blocks part of the light, making it difficult for human eyes or visible light telescopes to see what is happening inside. Yet within that darkness, matter continues gathering, the temperature continues rising, and a new source of light takes shape one step at a time. An ordinary image can make this easier to imagine. A newly developing neighborhood may appear almost completely dark at night. At first, there are only unfinished buildings, construction materials, dirt roads, and a few people working quietly. Seen from far away, very little stands out. But after some time, the first house turns on its lights. Then a second, and a third. A region that was once dark begins to show illuminated windows. The light did not appear from emptiness. It came after a long period of preparation that a distant observer could not clearly see. Star formation follows a similar rhythm. Cold molecular clouds contain large amounts of gas, especially hydrogen, along with dust. Here, the word molecular simply means that the material exists in a form that allows the cloud to cool and gather more easily. Within such a cloud, a region that is denser than its surroundings can become the seed of a new star. The entire cloud does not immediately turn into stars. Only certain parts reach the conditions needed to collapse more strongly and form young stellar cores. This process is not fast by human standards. A star like the Sun may take millions of years to form from a cloud of gas and dust. Millions of years sounds unimaginably long, but within the life of a galaxy, it is simply part of the natural rhythm. A galaxy does not create stars in a single moment. It nurtures them inside cold clouds, through gravity, through the gradual contraction of gas and dust, and finally through the moment when the stellar core becomes hot enough to begin shining steadily. When a young star forms, it does not immediately appear as a clean point of light against a dark background. Material left over from the original cloud still surrounds it. Gas and dust may continue falling toward the center, or they may form a disk around the young star. In some cases, planets may eventually develop from that disk. But the important idea here is simple. New light often begins while hidden. It is born in a place that ordinary vision cannot easily reach. This is why infrared telescopes are so important. Visible light is easily blocked by dust, making star-forming regions appear dark or faint. Infrared light, however, can pass through dust more effectively in many situations, allowing us to look into places where ordinary light is obscured. Through infrared observations, astronomers can detect young stars still buried within clouds of gas and dust, regions that are only beginning to brighten, and structures that visible light images cannot show clearly. This connects back to the curtains of dust described earlier. A curtain does not make the room behind it disappear. It only softens the light from that room, dims it, or changes the way it appears to us. Interstellar dust works in much the same way. It blocks part of the visible light, but behind it there may still be young stars, dense regions of gas, and places preparing to create new light. With the right kind of observation, the picture behind the curtain becomes clearer. In spiral galaxies, star-forming regions are often connected with the spiral arms. Gas and dust may be more concentrated there. As clouds of gas move through denser regions, they can be compressed, increasing the chance that stars will form. Spiral arms are therefore not only beautiful curves, they can also be active regions where a galaxy continues producing new generations of stars. Still, not every dark region is forming stars, and not every dusty area is guaranteed to contain new stars. Science requires additional observation to tell the difference. Astronomers examine whether cold gas is present, whether young stars are producing strong radiation, and whether the region shows the expected infrared or radio signals. Only by combining many forms of data can they determine which areas are truly forming stars and which are simply blocking the light behind them. This way of seeing helps prevent us from misunderstanding darkness in astronomical images. Darkness is not simply absence. Often, it is evidence of matter. Dust dims the light. Gas provides the material from which new stars form. Cold clouds create places where gravity can begin gathering that material together. And from those very regions that appear dark, new light may emerge after a very long time. A galaxy, therefore, contains more than stars that are already shining. It also contains places where future light is being prepared. There are old stars glowing more softly. There are young stars shining intensely. There are regions hidden by dust. There are cold clouds of gas that do not yet shine, but may one day become the birthplaces of stars. All of these parts together create the inner life of a galaxy. When we look at an image of a galaxy, bright and dark regions may appear side by side. At first, the bright areas naturally draw more attention. But once we understand the role of gas and dust, the dark regions become equally meaningful. They may be holding raw material. They may be hiding the process of star formation. They may be places where, far in the future, new sources of light will appear. The image is no longer a simple contrast between brightness and darkness. It becomes a layered system in which shadow also has a role. This creates a very special feeling. Light in the universe does not always begin with brilliance. Sometimes it begins in coldness, darkness, and silence. Before a star shines, millions of years may pass while matter slowly gathers in a region hidden from human sight. Before a cloud of gas begins to glow, it may spend ages contracting quietly under gravity. What appears to be an empty darkness in an image may actually be the first part of a story of light. From here, once a young star becomes hot and bright enough, it does more than shine on its own. Its powerful light can affect the gas around it, especially hydrogen, causing that gas to glow as well. At that moment, we do not see only the new star. We see the surrounding region of space being awakened with it. When a young star begins to shine, it does not produce light only for itself. Its powerful radiation spreads outward and affects nearby hydrogen gas, causing that gas to glow like mist illuminated in front of a lamp. In astronomical images, these regions often appear as soft patches of light, sometimes pink or reddish depending on how the telescope observes them and how the data is processed. These are H2 regions, places where radiation from young stars ionizes hydrogen gas, causing the hydrogen to glow and become a clearly visible part of the galactic picture. H2 regions are not always large or brilliant. Some are only faint patches of light between the stars. Yet no matter how small they mark places where stars are forming and where gas and dust are responding to the energy of newly born stars. By looking at them, observers see not only young stars shining, but also the effect those stars have on their surroundings. This is one way the universe tells the story of new activity taking shape within a galaxy. An everyday image can make this easier to imagine. Picture a lamp being switched on inside a room filled with a thin mist. The bulb does not shine alone. The mist around it also lights up, creating soft, glowing patches throughout the space. The mist does not generate its own light, but it becomes visible because of the light from the source. In a similar way, hydrogen gas within a galaxy does not normally glow on its own. But when it is energized by radiation from young stars, it begins to shine, forming bright regions around them. The presence of H2 regions also helps astronomers understand the process of star formation more clearly. By observing their color and shape, scientists can learn about the ages of nearby young stars, the density of the surrounding gas, and the rate at which ionization is taking place. Brighter regions often indicate very hot, energetic young stars. Fainter regions may suggest star formation at an earlier stage, or areas where less gas is present. In an image of a galaxy, we see a delicate combination of old and young stars, bright regions, and darker areas hidden by dust. H2 regions create a rhythm of their own across the larger picture. New light appears within gas-rich environments, highlighting areas of intense activity while standing in contrast to the surrounding darkness. This rhythm helps reveal spiral arms and allows astronomers to distinguish active regions from those that have become quieter. A galaxy, then, is not made only of stars that already exist. It is also a place where hydrogen gas is being awakened, where young stars are forming, and where different layers of matter interact to create new light. When we examine H2 regions closely, we begin to understand that even within darkness, a galaxy continues to grow, release energy, and tell the story of its inner life and evolution. Hi2 regions are places where newly born light emerges from darkness. They show that a galaxy is a dynamic system, where older starlight shapes much of the overall view, while new light from young stars gradually appears, creating vivid patches among the shadowed regions. Through them, observers can read both the history and the present state of a galaxy. Old stars, young stars, gas, dust, and the processes still unfolding within the dark. After looking at the regions of glowing hydrogen gas surrounding young stars, we begin to see one of the most active parts of a galaxy. These are places where new light is appearing, where enough gas and dust still remain to create future generations of stars. But a galaxy is not made only of young, intensely bright regions. Alongside newly born stars are countless older stars that have existed for a very long time, quietly preserving the history of the galaxy within their light. Within the same galaxy, not every star is the same age. Some have only recently formed inside cold clouds of gas. Others have existed for billions of years. Some are hot and extremely bright, producing light that appears more blue-white. Others are cooler or older, with light that leans more toward yellow, orange, or red. When all of this starlight blends together, it creates the overall color and character of each region within the galaxy. This allows astronomers to understand a galaxy not only through its shape, but also through the age of the light inside it. A region containing many young stars often shines more strongly in blue-white wavelengths. Young, hot stars usually consume their fuel quickly and do not live as long as smaller, cooler stars. So if one part of a galaxy contains a great deal of blue light from young stars, it may suggest that star formation is still taking place there, or has happened there very recently. Regions containing more old stars often produce softer, quieter light. That light is not necessarily faint, but it has a different quality. It appears less explosive, with fewer intense blue tones. It feels steadier and more settled. In many galaxies, the central region or bulge may contain large populations of older stars, giving it a warmer color than the outer arms, where younger stars and glowing clouds of gas may stand out more clearly. We can imagine a city seen from above at night. In a newly developed district, glass towers, bright signs, wide roads, and strong white lights may make the entire area appear sharper and more vivid. In an older neighborhood, the lights may be warmer, lower, and more evenly spread, shining from small windows along narrow streets. Both are parts of the same city. Both contain life. Yet their light gives us a sense of different layers of time. Galaxies also contain layers of time like these. Young stars are like new lights switching on in a growing neighborhood. Old stars are like lamps that have continued shining through countless long nights. They may not attract as much attention as brilliant star-forming regions, but they are deeply important. They reveal that the galaxy has a long past, that stars formed there during earlier periods, and that those older generations still contribute their light to the present view. Our own sun offers a familiar example. It is about 4.6 billion years old. On the scale of a human life, that number is almost impossible to grasp. But within the history of the Milky Way, the sun is only one member of many generations of stars. Other stars were born, lived, and ended before the sun existed. And after the Sun, new stars may continue forming in other regions of gas and dust. A galaxy is therefore not a collection of stars born at the same time, but a place where many generations coexist. By studying the colors of a galaxy, astronomers can infer part of its history of star formation. If a galaxy still contains many bright blue regions, along with abundant gas and dust, it may still be producing new stars at a strong rate. If a galaxy has redder, more evenly distributed light and fewer prominent gas-rich regions, it may have passed through its most active period of star formation long ago and become quieter in the present. This is not a conclusion that can be made simply by looking with the naked eye, but color is an important clue from which analysis can begin. The locations of young and old stars within a galaxy are also meaningful. In many spiral galaxies, the outer arms contain more gas, dust, and star-forming regions. Because of this, they may contain many bright young stars. The central region or bulge, by contrast, may contain more old stars with steadier light. This distribution reveals that a galaxy has internal structure rather than being a uniform patch of brightness. Old stars are not the parts of a galaxy that have lost their value. They are the memory of earlier stages. Their light shows that matter once gathered there, that stars once formed there, and that processes continued for billions of years. If we focus only on young stars and the brightest regions, we see only the active present. But when we also look at old stars, the historical depth of the galaxy begins to emerge. A galaxy can therefore be compared to a city inhabited by many generations. Some districts are new and still under construction, filled with bright lights and movement. Others are older and more settled, with softer but more enduring light. Some areas are changing, while others have become quiet. Seen from far away, all the lights blend together. But if we learn to distinguish the glow of young regions from the glow of older ones, we begin to understand how the city has grown through many different stages. In astronomical images, these differences may be extremely subtle. One region may be only slightly bluer. Another may be only slightly more yellow. A central area may appear only a little more evenly illuminated. Yet these small differences can reveal a great deal. They help observers identify where new stars are forming, where older stars are more abundant, where dust is blocking part of the light, and where star formation has become quieter. The light of older stars also helps balance the way we understand galaxies. The universe is not only a place where new things are constantly bursting into brightness. It is also a place where older things continue to exist, continue to shine, and continue to preserve the marks of time. An old star may not stand out as strongly as a hot young star, but it remains part of the larger structure. It contributes to the galaxy's overall glow, its color, its brightness, and its sense of history. When we return to the original faint blur, another layer of meaning becomes visible. If that blur is the light of a galaxy, it does not contain only one kind of light. It may include young light from star-forming regions. It may contain the quieter glow of older generations of stars. Dust may hide part of that light. Gas may be preparing to form future stars. All of these things blend together, travel across an immense distance, and finally reach us as one small patch of brightness. This makes a faint streak far richer than it first appears. It is not merely brightness. It is the combined light of many generations of stars. It does not only tell us that an object exists far away. It may also contain clues about that object's age, history, and development. A galaxy, even when seen only as a blur from a great distance, may still carry within it the light of the past, the present, and the possibility of the future. From here, the story of the galaxy begins to move deeper into its internal structure. We have seen the spiral arms, the dark regions of dust, the places where young stars form, the glowing hydrogen gas, and the older lights of long-lived stars. But in many galaxies, the light is not distributed evenly from the inside outward. Some regions are denser and more crowded with stars, especially near the center. And as we move toward that center, we encounter one of the most important parts of many galaxies, a bright, densely packed region where stars gather like the crowded old neighborhoods of a city. Many galaxies have more than spiral arms and outer regions. They also contain a bright, densely packed center. If we imagine a galaxy as a city, the central region is like an old historic district. The streets are narrower, the windows are closer together, and the lights are more concentrated. Older stars are often more abundant there. The density of matter is greater, and the combined glow is stronger than in the outer parts. When we look toward the center, individual stars can become difficult to separate, their light blending into a round or slightly oval region of brightness in the image. The spiral arms extend outward around it, but the central region usually contains a much higher concentration of stars. This is more than a visual feature. It is a place that preserves many layers of history. Many of the older stars there have existed for billions of years. Some formed from ancient clouds of gas. Others have occupied the inner region for an immense span of time, creating light that is quieter in color but steady and enduring. The central bulge is therefore not only brighter, it is also a record of the galaxy's development. Astronomers use light and color data to learn more about this central region. Older stars often shine in yellow, orange, or red tones, while younger stars in the outer arms tend to appear more blue-white. By observing the center, we can see differences in stellar age, color, and density, allowing astronomers to identify regions that may have passed through many periods of star formation. An everyday image can help us picture this. Imagine a city seen at night in a satellite image. The center is densely illuminated, with light concentrated among closely packed buildings. The suburbs are more spread out, with fewer and weaker lights. Beyond them, the glow gradually fades into darkness. These differences in brightness and density give us a sense of distinct regions, each belonging to the present while also preserving part of the city's history. Near the center of a galaxy, there may also be a deep and heavy region that produces very little light of its own, yet remains important. It may contain large amounts of dust, gas, or material that has not formed new stars. By combining observations of the spiral arms, H2 regions, young stars, and old stars, we can begin to recognize the overall structure of a galaxy, a dense center, extended arms, and alternating regions of light and shadow. In this way, the picture of a complete city of stars gradually appears before the observer. The bright, crowded center helps astronomers estimate the mass of a galaxy, the density of its matter, and the way its stars are distributed. This is also the region where a supermassive black hole is often found. But even without focusing on the black hole, the central bulge reveals a powerful and stable structure with a very long history, where stars gather closely and their light blends together, much like an old district that preserves its basic form even as the city around it changes. By studying the center, astronomers can learn more about galactic evolution, the balance between old and young stars, and the way a galaxy preserves its central structure over billions of years. This is an important step in understanding that a galaxy is not merely a scattering of bright points, but an organized system with many layers and many generations of stars, extending from its densely packed center to the spiral arms reaching outward around it. At the center of many large galaxies, including our own Milky Way, lies a remarkable object, a supermassive black hole. This black hole is not an invisible monster pulling the entire galaxy into itself. Its influence is extremely strong nearby, but stars farther away continue following their own orbits instead of falling directly into the central region. At the center of the Milky Way, this black hole is called Sagittarius A. It has a mass of about 4 million suns. For many years, astronomers have observed the motion of stars close to the galactic center, measured their orbits around the dark region, and used those movements to confirm that an enormous concentration of mass is resting there. An everyday image can make this easier to understand. Imagine a deep well in the courtyard of an old neighborhood. Standing too close to the edge could be dangerous. But the houses around it do not suddenly slide into the well simply because the well exists. In much the same way, a black hole has its strongest influence close to the center. Stars farther away continue moving normally and remain part of the galaxy's overall structure. The dense central region where Sagittarius A lies is one of the most important parts of many galaxies. It contains a high concentration of stars, most of them old, though some young stars may also be present. This region preserves many layers of galactic history, much like the center of an ancient city, where the streets are narrow, the buildings crowded together, and the lights densely packed, yet the city as a whole remains organized. One important thing to remember is that a black hole does not pull an entire galaxy into itself. It creates a powerful gravitational field nearby and shapes the orbits of stars close to it, while the outer regions continue rotating under the galaxy's overall gravity, just as the houses around a well remain standing. Because of this, the galaxy keeps its structure. Its spiral arms, dusty regions, and star-forming areas continue to exist. These observations help us understand that a galaxy is not simply a still image. Its dense center contains a great deal of mass and also plays an important role in the galaxy's structure. It influences nearby orbits, affects the distribution of stars, and provides clues about how the galaxy formed and developed. Telescope images, measurements of stellar orbits around Sagittarius A, and the presence of a supermassive black hole all reveal that a galaxy has a stable order, with light and matter moving according to consistent physical laws. Even when the center appears dark like a deep well, the rest of the city of stars continues to function, preserving its spiral or rounded shape. For the observer, understanding the galactic center and its black hole reveals something important. The dark central region is not simply empty, nor is it entirely destructive. It has structure, mass, and gravitational relationships with the surrounding stars that exist within the galaxy's broader balance. Because of this, the Milky Way and other galaxies continue to endure, rotate, form stars, and extend their arms into the darkness without being swallowed whole. Once we understand this, the bright streaks and dark regions in an image of a galaxy no longer seem merely bright or dark. They show us how the central black hole influences nearby stars while reminding us that most of the galaxy continues to exist independently, preserving its structure and continuing to form new stars. The center is both dark and luminous, dense and complex, yet it does not destroy the entire galaxy. It is like a deep well in the middle of an old neighborhood, mysterious, but unable to erase the life continuing all around it. The central region of a galaxy is both bright and dark, densely packed yet filled with faint shadowed areas. At first glance, a galaxy seems motionless. Its spiral arms and stars appear silent against the darkness. In reality, however, the entire galaxy is rotating from the center to the outer regions. Stars, gas, and dust follow their own orbits, creating a slow-turning motion that cannot be perceived in a single moment. When astronomers measured the motion of stars, they discovered something unusual. In the outer regions of galaxies, the rotational speed did not decrease as expected. According to ordinary physical laws, objects farther from the central concentration of mass should move more slowly. Yet the stars continued traveling at high speeds, as though additional invisible mass were holding them in orbit. This suggested the existence of dark matter, a form of mass that does not produce light but still has a powerful effect on the motion of a galaxy. The central region remains densely filled with stars and concentrated light. But the central black hole, despite its great strength, does not pull the entire galaxy inward. Stars farther away continue orbiting the center. Spiral arms, regions of gas and dust, young stars, and old stars all continue moving together. The black hole dominates only the region closest to it, like a deep well in the middle of an old neighborhood. Stars near the edge of the well move more quickly, but the surrounding district continues functioning normally, preserving the structure of the entire city of stars. This helps us understand that a galaxy is more than a collection of bright points in an image. It is a living system in which stars move along orbits, gas and dust are distributed through gravitational patterns, spiral arms extend outward, and the central region contains a black hole without allowing it to destroy the whole galaxy. By studying rotation curves and the motion of stars, observers recognize that mass, which does not shine, is still present, helping to keep the galactic structure stable. Within an image, bright regions, dark regions, old stars, young stars, gas, and dust all blend together, forming a system that is complex yet ordered. The faint streaks beyond the spiral arms are not errors in the image. They reflect matter that truly exists, while also suggesting the influence of mass that produces no visible light but still affects the stars nearby. The rotation of a galaxy acts like a quiet revelation. It tells us that dark regions are not necessarily empty, that stars are not standing still, and that light does not exist in isolation. A large part of the galaxy remains active even when the naked eye cannot see it. By understanding motion and gravity, observers can begin reading the story of the galaxy's structure, history, and balance. This knowledge gives greater depth to an image of a galaxy. It is no longer only a picture of bright arms or a densely luminous center. We understand that light from old stars, young stars, gas, and dust all contributes to the whole, while an invisible component of mass helps keep everything in orbit. The galaxy is not still. It turns slowly, preserves its structure, and creates the rhythm of a city of stars. From here, the story expands to the larger system. If one galaxy can preserve its structure while rotating and continue holding stars at every distance, then the universe is filled with systems that work in similar ways. Matter that does not shine still shapes motion. Over immense periods of time, galaxies interact, collide, and sometimes merge. After recognizing the internal structure of a galaxy and the presence of dark matter, the next step is to look at the relationships between galaxies. Galaxies do not exist in complete isolation. They move through space, feel one another's gravity, and sometimes draw closer in ways that leave visible marks in the light and matter recorded by astronomical images. A familiar comparison would be two cities separated by several dozen miles. Each city continues to function on its own, yet highways, bridges, and the movement of people between them allow the two places to interact. Galaxies behave in a similar way. Even when they are separated by millions of light years, gravity can still draw them toward one another. In images, the light from stars and gas may reveal signs of this interaction. Spiral arms can become stretched or displaced, while regions of gas and dust may be scattered in the direction of the neighboring galaxy's influence. When two galaxies move close to each other, the motions of their stars can also change. Stars near the outer edges may be pulled farther outward, creating distorted shapes and shifting them away from their previous orbits. Gas and dust may also be redistributed, producing new faint bands within an image. These are some of the signs astronomers use to recognize that galaxies are interacting, colliding, or gradually moving toward a merger. An everyday image can help us picture this. Imagine two rivers flowing near each other. At first, each follows its own separate path. When they meet, their waters begin to mix, their currents affect one another, and whirlpools appear. Even though parts of each river may still remain distinct, the interaction creates curved patterns and regions where the water changes direction. Galaxies behave in a similar way. Each retains some of its own structure, but the gravity of the other can distort it, stretch it, or pull it out of alignment. One important effect of these close encounters is the compression of gas. When two galaxies pass near each other or experience a gentle collision, clouds of gas within them may collide or become crowded together. This compression can encourage the formation of new stars, producing bright clusters in regions that were previously dark. This is why newly luminous areas often appear along the arms or outer edges of interacting galaxies, making the image seem more active and complex. Astronomers have also discovered that interactions between galaxies do more than distort their visible shapes. They can reveal the amount of dark matter surrounding them. As galaxies approach one another, the orbits of stars and gas are altered by invisible mass that cannot be seen directly. By analyzing these motions, scientists can estimate how dark matter is distributed and learn more about the evolutionary history of the galaxies involved. When we look at pairs of interacting galaxies, it becomes clear that the universe is not static. It is a dynamic system in which objects are constantly moving, influencing one another, and changing over time. The light we see from stars and gas does not only tell us where those objects are, it also preserves evidence of interactions that may have continued for millions of years. This is also why galaxies within the same galaxy cluster can have very different shapes. A galaxy near the center of a cluster may experience stronger gravitational forces and become more heavily distorted. A galaxy near the outer edge may preserve its spiral form more clearly. By observing many galaxies within the same cluster, astronomers can compare the changes caused by interaction and begin to recognize how gravity behaves on very large scales. Once we understand this, the bright streaks and dark regions in an image no longer appear as fixed shapes. We begin to see a galaxy as a rotating city that is also being influenced by neighboring cities. Its spiral arms may shift, dust may be moved, and stars may enter new orbits. Every detail carries part of the story of the galaxy's interaction and its long history of motion. From here, the cosmic picture begins to widen. We no longer see only one isolated galaxy, but entire systems of galaxies moving, interacting, colliding, and gradually merging under the influence of gravity. New bright regions are born, dark regions remain, and spiral arms become stretched. Light continues traveling across space, preserving the record of each movement, each encounter, and each transformation. For the observer, this creates a sense that the universe is both vast and deep. Galaxies do not simply rest against a black background. They rotate, influence one another, and through those interactions create new shapes, changing regions of light and shadow, while signs of dark matter quietly reveal the invisible mass helping to guide their motion. Seen as a whole, the universe is not merely a collection of bright points, but a living and complex network in which every object participates in a shared cosmic rhythm. A giant galaxy is not born giant. It grows over billions of years, layer upon layer, with each generation of stars adding depth to its history. A galaxy forms new stars from cold gas, preserves older stars, and gathers more material from its surroundings. It may absorb smaller galaxies, much like a growing city gradually taking in villages along a river, expanding its boundaries and increasing the density of its stellar population. Astronomers read that history through many clues: the ages of the stars, their speeds of motion, the amount of gas and dust that remains, and the chemical composition of the stars themselves. Each star is a fragment of memory. Each bright region represents a period of development. Each dust lane or distorted streak of light may be the trace of an ancient encounter with another galaxy. Together, these details tell the story of how a galaxy was born, how it grew, and how it interacted with the environment around it. An everyday image can make this easier to imagine. Picture a village beside a river gradually gaining more houses, more bridges, and a larger marketplace. Over many generations, the village becomes a city with new roads, expanding neighborhoods, and bridges connecting different communities. A galaxy grows in much the same way. It does not become vast in a single moment. Over billions of years, new layers of stars and gas are added, smaller galaxies are merged into it, and repeated periods of star formation create the width and depth of the entire system. Some galaxies began forming very early in cosmic history, only a few 100 million years after the Big Bang. Their earliest stars are now extremely old and may shine more faintly. But over billions of years, cold gas continued producing new stars, the galaxy preserved older generations, absorbed material from other galaxies, and gradually developed the complex structure we observe today. The history of a galaxy is therefore recorded in every light, every color, and every movement of the stars within it. There is something profound in realizing this. A galaxy is not only a spiral or an oval shape. It is not only a set of curved arms or a bright central region. It is a long story in which generations of stars, collisions, and periods of star formation follow one another through layer after layer of time. The light we see today comes not only from the place where the object exists, but also from stages that have already passed, preserving traces of the galaxy's entire evolution. Among the countless galaxies beyond us, one is especially important. Not because it is the largest, but because we live inside it. The Milky Way is the galaxy we call home. It is more than a system of stars, gas, and dust. It is a history in which we directly participate. Every star we see, from the sun to stars far beyond the reach of our eyes, is part of a long process in which the galaxy grew through layers of time, gathered material, formed new stars, and preserved the remains of earlier generations. So when we look into the sky and notice faint streaks of light, we are not seeing only points in space. We are seeing stories that have unfolded over billions of years. Stories of galaxies forming, growing, interacting, and recording each stage through generations of stars, clouds of gas, spiral arms, and the quiet presence of dark matter helping to preserve their order. Every layer of time is carried in light, and every star is evidence that a galaxy grows continuously, step by step, through every age of the universe. The Milky Way is the galaxy that contains our solar system, the place where we live. What makes it unusual is that we cannot travel outside it and photograph the entire galaxy the way we observe other galaxies. Imagine standing inside an enormous house. We can see the hallways, a few rooms, and light entering through the windows, but we cannot step outside to view the entire roof or the complete shape of the building. Everything visible to us is only one part of the whole. The rest must be reconstructed from what we are able to observe. To create a map of the Milky Way, human beings must combine many different pieces of data. Astronomers measure the positions of individual stars, follow their motions, and record hydrogen gas, dust, star clusters, and regions of star formation. One important tool is the Gaia mission, a project of the European Space Agency designed to measure the positions, distances, velocities, and colors of billions of stars, providing data that helps create a three-dimensional map of the galaxy. When all of this information is combined, astronomers can build a three-dimensional model of the Milky Way. Because we live inside the galaxy, the images found in books and simulations are not direct photographs taken from outside. They are the result of carefully assembling many small observations to form a picture of the galaxy as a whole. The Milky Way is about 100,000 light-years across. The Sun lies roughly 26,000 light-years from the galactic center. These numbers help us understand the scale, but the idea becomes more personal when we imagine ourselves standing among billions of stars, looking toward a distant band of faint light, and realizing that we are one small part of an enormous system filled with structure and history. An everyday image can make the Milky Way easier to understand. A person standing inside a large house may see the nearby walls, a staircase, the hallways, and light entering through a window. To understand the overall shape of the house, that person must rely on floor plans, separate observations, imagination, and experience. The Milky Way is reconstructed in much the same way, from data gathered from old stars, young stars, gas, dust, and densely crowded central regions. We live inside the galaxy, so we must observe, measure, and assemble these separate pieces before we can imagine its complete structure. This creates a feeling that is both intimate and profound. After traveling through faint streaks of light, spiral arms, luminous central regions, dark clouds, and the processes of star formation, we begin to realize that we are living within this very kind of galaxy. Every night when we look upward, all the light we see belongs to the enormous home we have never left. Every star, every glowing region, and every cloud of dust is part of a story that we are living inside. Seen from within, the Milky Way feels close and familiar, like a house whose hallways we have walked through, whose floors we have crossed, and whose window light we have watched flicker. But if it were viewed from far away, this entire home might appear as nothing more than a faint blur, a pale streak against the darkness. This helps us understand that the models of the galaxy shown in books and simulations are created by assembling observational data, and that they represent something far larger than anything our eyes can see directly. The layers of time within the galaxy are revealed through every star and every cloud of gas. Old stars carry the memory of earlier stellar generations, while young stars and regions of gas reflect activity taking place now. The spiral arms, the central region, and the dark, dusty areas are more than patterns of light. They are remains of history, stages of development, and traces of interactions with neighboring galaxies, all contributing to the overall shape of the Milky Way. Standing within this enormous home, we can sense its depth and activity. We are not merely observers looking in from outside. The place where we stand within the galaxy, and every light our eyes can see, belong to a much larger structure. We see the present while also recognizing a past preserved in starlight. Layers of time overlap to create a picture that is complex yet ordered, and we ourselves exist inside it. If the Milky Way were viewed from outside like another distant galaxy, the whole system might appear only as a faint patch of light. But from within, we know that this glow contains billions of stars, countless layers of gas and dust, densely crowded central regions, and processes that have unfolded over billions of years. We are living inside an immense story in which every layer of time, every star, and every cloud of gas contributes to the shape and light we observe each night. Because of this, every image, model, and map of the Milky Way is more than scientific information. It is humanity's way of recording, recreating, and understanding the enormous home in which we live. We are residents, observers, and parts of this larger picture all at once. Every region of light and shadow carries information about the past, the present, and the possibility of future star formation. The Milky Way is therefore more than the galaxy that contains the solar system. It is the story of a living system that humanity experiences from within. Once we understand that we are living inside the Milky Way, the way we see a faint streak of light in a deep space image begins to change. At first, we look at a distant blur and wonder what may be hidden inside it. Perhaps it is a galaxy. Perhaps it contains young stars, old stars, gas, dust, regions of darkness and light, and a history stretching across immense spans of time. But after returning our attention to the Milky Way, we recognize something much closer to home. If someone very far away were looking toward our galaxy, they too might see nothing more than a faint streak of light. From within, the Milky Way is the great home of the Sun. It contains the solar system, Earth, the atmosphere, oceans, clouds, mountains, cities, and every familiar form of human life. But from an immense distance, none of those details would appear separately. Earth would not stand out as a clear blue point within the combined light of the entire galaxy. The Sun would be only one among countless stars, and the whole Milky Way, even though it spans roughly 100,000 light-years, could still appear in a distant image as one small, luminous structure. This does not make Earth any less meaningful. It simply shows how distance can make everything appear very small within our field of view. A place containing all of human life can become only a tiny contribution to the glow of a galaxy. A planet may have oceans, rain, wind, and rooms glowing with light at night, yet from far beyond the galaxy, none of those things would remain visible as separate details. They would blend into the light of the planet's parent star, and that star would then blend into the combined light of the galaxy. We can imagine an apartment building seen from very far away at night. Standing nearby, we can distinguish individual balconies, windows, and lamps inside the rooms. In one apartment, someone may be cooking. In another, someone may be reading. Somewhere else, the lights have already been turned off for sleep. Every illuminated window contains a separate life, with its own sounds, habits, memories, and stories that no one outside can fully know. But from a great distance, the entire building becomes only a few small points of light. The distant observer cannot know what is happening behind each window. They see only the glow. The Milky Way could appear much the same to an observer extremely far away. The sun would be somewhere within that streak of light, but the observer would not see it separately with the naked eye. Earth would also be there, but far too small to distinguish from the entire system. And on Earth there would still be oceans, forests, clouds, cities, mornings, evenings, and sleep. Yet across intergalactic distances, all of those things would remain hidden within an unimaginably small part of the galaxy's total light. This way of seeing helps us understand the entire journey from the beginning. When we notice a faint blur in a deep space image, we should not immediately assume that it contains very little. There may be individual worlds within that blur. There may be stars illuminating planets. There may be clouds of gas producing new stars. There may be densely packed centers, spiral arms, and dark layers of dust blocking part of the light. From far away, all of this is gathered into one faint region. But inside that dim glow, structure and history may still exist. An astronomical image, therefore, carries two emotional dimensions. In one sense, it makes us feel very small. Earth is not at the center of the universe. The sun is not the only star. The Milky Way is only one galaxy among countless others. Seen from a great enough distance, the place we call home might appear as nothing more than a faint streak in someone else's image. Yet this feeling does not have to be cold or lonely. It can also make the universe seem deeper, because even the smallest blur may contain an extraordinary richness within it. From very far away, no one would see a person standing beside a window and looking into the sky. No one would see an open book resting on a table, a cup of water, a quiet room, or a soft voice in the night. Yet all of those things would still be real. They do not disappear simply because distance prevents them from appearing in an image. In the same way, when we see distant galaxies as blurred patches, we cannot see everything inside them. But that does not mean their interiors are simple. This is what makes the story of faint streaks feel more personal. At first, we stand in the position of the observer. We look at a small mark near the edge of an image and try to understand it. But now, we can also imagine ourselves living inside a mark just like it. We inhabit a galaxy that distance could soften into a blur. We are familiar with every passing day on Earth, yet through a telescope placed unimaginably far away, all of human life would occupy only an inseparable part of the Milky Way's light. This also reminds us to be careful with the feeling of smallness. Small in an image does not mean small in reality. Faint in an image does not mean empty. A point of light may be a star. A soft blur may be a galaxy. A dim patch may contain billions of stars. And around one ordinary star, there may be a planet turning quietly, carrying stories that no distant observer could recognize. If someone far away were observing the Milky Way, they might see only a luminous structure surrounded by darkness. They might measure its color, brightness, shape, and motion. They might identify it as a barred spiral galaxy with a central region, stellar arms, and lanes of dust. But they would not see individual rainstorms on Earth. They would not see the oceans reflecting sunlight. They would not see cities glowing when night arrives. They would not see a person sleeping in a small room beneath a sky belonging to that same galaxy. From this perspective, the Milky Way is both enormous and small. It is enormous to us because no human being could cross it within a lifetime or step outside it to see the whole structure with their own eyes. Yet it is small within the universe because it is only one among an immense number of galaxies. This thought does not need to overwhelm us. It only asks us to look more slowly. Whenever a distant object appears as a faint blur, we can remember that our own great home might look exactly the same when viewed from far enough away. And so the journey that began with a dim mark near the edge of an image returns to us. At first, we asked, "What is that faint blur?" Now we can ask something more. If our own Milky Way is also only a faint blur to someone very far away, how much might be hidden inside every other blur that we cannot yet see? That question does not need an immediate answer. It simply opens a gentler way of looking at the universe. A galaxy is not merely light in an image. It is a combination of stars, gas, dust, gravity, time, and regions we do not yet fully understand. The Milky Way is no different. Within its combined glow are the sun, earth, and everything familiar to us. If, from a great distance, all of that becomes only a faint streak of light, then that streak is still far from empty. It contains a home. When we think of it this way, the deep images of the universe begin to feel warmer. The faint marks no longer seem entirely unfamiliar. They may be enormous homes viewed from distances too great for their details to survive. And Earth, hidden within the total light of the Milky Way, reminds us that smallness does not erase meaning. A single illuminated window in a distant apartment building still contains a life. A very small planet within a very large galaxy can still be the place where all of our stories unfold. From here, the story can begin to slow. We have traveled from a faint mark to a galaxy, from a galaxy to the Milky Way, and from the Milky Way back to Earth. After all of that, what remains is not another new concept, but a quiet feeling settling before the vastness. The universe does not always need to appear in brilliance. Sometimes it needs only one very small streak of light, enough to remind us that even within the faintest things, an entire world may be waiting. Our journey began with a faint mark near the edge of an image. At first, it was only a pale point of light, almost too subtle to notice. We did not know what lay inside that glow, how far its light had traveled, or what story it carried. Then we began to understand that the streak might appear faint simply because the distance was so great. Human eyes are too small to gather enough of that light. They cannot see the entire story in a single moment. Only through patient observation does its depth begin to emerge. The telescope appeared like a large bowl, quietly collecting each tiny photon, each fragile ray of light arriving from the most distant places. Photon by photon, that light may be like a letter that has traveled for millions of years, carrying traces of time and space, preserving the history of stars, gas, dust, and even the smaller galaxies nearby, before finally bringing us the story of the galaxy itself. Imagine an old photograph in which a small detail near the edge seems almost meaningless at first. But when the image is enlarged, examined carefully, and assembled with other observations, that detail is no longer secondary. It becomes a place where the entire story is preserved, where every motion, every episode of star formation, and every layer of gas and dust records part of the galaxy's history. Through this, we come to understand that the universe does not always reveal itself through brilliant or easily recognizable images. Many important things first appear only as faint marks against the darkness. But when observed for long enough, that dim feature may reveal a galaxy containing many layers: the light of young stars, the glow of older stars, dust, gas, motion, distance, and time. A weak streak of light is not necessarily a poor or empty detail. It may simply be the small part that reaches us from a structure far greater than anything we can see directly. Its value, then, does not depend on its apparent size or how strongly it stands out. A tiny streak of light may contain billions of stars, many layers of time, and a history extending across millions of years. Faint does not mean empty. Small does not mean meaningless. Even the palest and most indistinct details, when read with enough patience, can tell an enormous story. The universe may approach us very gently, but what appears in silence is no less vast. It takes patience to recognize it. It teaches us that everything, no matter how small or faint, has its own value and its own story. The tiny streaks in astronomical images, the barely visible marks, can still open into an entire galaxy when we look long enough and slowly enough. The universe does not always need to shout in order to be present. Sometimes it arrives almost silently while still carrying a story of unimaginable scale. In the end, the universe does not need to be brilliant or loud to tell its stories. It speaks through small points of light, blurred streaks, and subtle motions carried to us by light. And within each of those faint signals, we begin to recognize the vastness, activity, and immense history of the place that we ourselves call home, the Milky Way.